In 2026, the four biggest tech companies will spend around $725 billion on infrastructure. A single data center in Memphis draws 946 megawatts. In part 1, we covered how a GPU works. This is what's actually running out there right now, and who owns it. We'll go through every current NVIDIA data center GPU with real numbers, then AMD, Google, and Amazon's own silicon, then how these things are wired together, and finally the superclusters and what all of it costs. Here is NVIDIA's data center line. A 100 in 2020, 80 gigabytes of HBM2E at 2 terabytes a second, 400 watts. H100 in 2022, same capacity, but HBM3 at 3.35 terabytes a second and 700 watts. H200 in 2024 jumped to 141 gigabytes. B200 in 2025, 192 gigabytes at 8 terabytes a second, and around a kilowatt. And Rubin, arriving now, moves to HBM4 at 22 terabytes a second. In 6 years, 3.5 times the memory and 11 times the bandwidth. Before we go further, one thing you need to know to read any of these numbers. NVIDIA's headline flops figures are quoted with sparsity, a trick that assumes half the weights in your matrix are zero. The footnote is always there, in tiny text. The honest dense number is exactly half. So H100 is not 4,000 teraflops of FP8, it's 1,979. Every figure in this video is the dense one unless I say otherwise. H100 versus H200 is the cleanest experiment in the whole industry. Same silicon, same die, same 700 watts, and identical compute, 989 teraflops either way. The only thing that changed was memory, 141 gigabytes instead of 80, at 4.8 terabytes a second instead of 3.35. And inference got up to nearly twice as fast. That is the proof that memory bandwidth, not compute, is the limit for running large models. Blackwell, the B200, did something new. It isn't one chip, it's two dies bonded together and presented to software as a single GPU, joined by a 10 terabyte per second link. 208 billion transistors, and 9,000 teraflops of dense FP4. NVIDIA had hit the reticle limit, the largest piece of silicon a lithography machine can physically print. The only way forward was to use two. And then they went a step further. GB200 NVL72 put 72 Blackwell GPUs and 36 Grace CPUs into one rack, all connected over a single NVLink fabric at 130 terabytes a second. That's 5,184 copper cables, around 2 miles of copper in one cabinet. The unit of sale stopped being a chip. It became a rack. Rubin is next. 288 gigabytes of HBM4, 22 terabytes a second of bandwidth, NVLink doubled again to 3.6 terabytes a second, and 35 petaflops of dense FP4 for training, per GPU. A Rubin rack is expected to sell for somewhere between $5 and $7 million. AMD's answer is the Instinct line, and their pitch has always been memory. When H100 shipped with 80 gigabytes, MI300X had 192, enough to fit a 70 billion parameter model on a single card. MI325X took that to 256, and MI355X to 288 gigabytes at 8 terabytes a second. Note that AMD quotes MI355X with sparsity too, so have their headline for the dense figure. And in February 2026, Meta committed to deploying up to 6 gigawatts of AMD capacity, with the first gigawatt shipping in the second half of this year. That's the first time a hyperscaler has bet at that scale on something other than NVIDIA. But the most under-discussed competitor is Google, because Google barely buys GPUs at all. Their 7th generation TPU, Ironwood, does 4,600 teraflops of FP8 per chip, with 192 gigabytes of memory at 7.4 terabytes a second. And they connect 9,216 of them into one pod using optical circuit switching, 442 exaflops. Google designed their way out of the queue everyone else is standing in. Amazon has Trainium, now on its 3rd generation at 2.5 petaflops per chip on TSMC's 3nm process. Microsoft has Maya, Meta has MTIA for ranking in ads. And Google's total fleet is estimated at around 5 million H100 equivalents, roughly a quarter of all AI compute on the planet, in one company's hands. So the market looks like this. NVIDIA around 80% of accelerator revenue, custom in-house silicon about 13, AMD around 6, Intel about 1. But the interesting part is the direction. Custom chips are the fastest growing slice, because the biggest buyers would all rather design their own than pay NVIDIA's margin. Now, how do you connect them? NVLink started at 160 gigabytes per second on the P100 back in 2016. 300 on V100, 600 on A100, 900 on H100, 1800 on Blackwell, and 3600 on Rubin. 22 times faster in 9 years, and it is still the bottleneck. There are actually 2 separate networks in every AI cluster. Inside the rack, it's NVLink over copper at 1.8 terabytes a second per GPU, but copper only reaches about 2 meters at these speeds, which is exactly why NVL72 is 1 rack and not 2. Between racks you switch to optical, InfiniBand or Ethernet, at around 800 gigabits per second per GPU. Scale up and scale out. Completely different technologies. And here is why this matters more than anything else. On real training runs, the all-reduced step, where every GPU shares its gradients, has been measured consuming up to 94% of each step on Ethernet clusters, and up to 75% even on InfiniBand. Your GPUs spend most of their time talking, not computing. So the industry rebuilt Ethernet. Ordinary data center Ethernet delivers roughly 60% of its rated bandwidth under this kind of load. AI-tuned Ethernet claims around 95, using per-packet spraying, adaptive routing, and proper congestion control. Some switches now even do the reduction arithmetic in flight, inside the network, so the data never has to make the round trip. Networking is roughly 15% of the total cost of a modern cluster, and about 60% of that is just the optical transceivers. NVIDIA's networking division alone booked $11 billion in a single quarter, up 263% year-on-year. The interconnect became a business the size of a large company. Which brings us to the machines themselves. xAI's Colossus 2, 946 megawatts, 440,000 Blackwell chips, an estimated $35.8 billion. Amazon and Anthropic's Project Rainier, 910 megawatts running over 1 million Trainium chips. Microsoft's Fairwater in Atlanta, Meta's Prometheus, OpenAI, and Oracle's Stargate in Abilene, each one of these draws the electricity of a small city. To put Colossus 2 in perspective, 440,000 GPUs is more compute than existed in the entire world a few years ago, in one building, in Memphis, with its own gas turbines because the grid could not supply it fast enough. And yet the single largest owner of AI compute isn't any of them. It's Google, around a quarter of all AI compute on Earth, roughly 5 million H100 equivalents, almost all of it TPUs they designed themselves and never sold to anyone. The growth rate is the part that's genuinely hard to believe. Since August 2024, the compute in the largest single AI data center has doubled roughly every 7 months. That's about 3.3 times per year, sustained, for 2 years. So what does this cost? An H100 is $35,000 to $40,000. AB200, $30,000 to $50,000. A GB200 NVL72 rack is around $3 million for the cabinet. And Rubin racks are expected between $5 and $7 million each. Most people rent instead. And the spread is remarkable. The same B200, per GPU hour, runs about $4.28 on Google Cloud, $6.69 at Lambda, $7.15 at Nebius, $8.60 at CoreWeave, and over $14 on AWS. Identical silicon, a 3 times price difference depending purely on where you buy it. Zoom out and the numbers stop making intuitive sense. The Big Four hyperscalers guided to roughly $725 billion of capital spending in 2026, up about 77% in a single year. NVIDIA's data center division alone booked $193.7 billion. And OpenAI has committed to something like $1.4 trillion of compute, around 30 gigawatts of capacity. There's one accounting argument worth knowing about, because a lot rides on it. How long does a GPU actually last? Amazon depreciates over about 4 years. Most hyperscalers use 5 to 6. Meta has stretched to 11 or 12. That choice massively changes reported profit, and if the real useful life turns out shorter than the schedule, a lot of earnings were overstated. Nobody knows yet. And finally, a detail most explanations skip. Running a model isn't one workload, it's 2. Reading your prompt, prefill, is compute-bound and hammers the tensor cores. Generating each token to decode is bandwidth-bound, because the model has to reread its own weights for every single word. One chat message uses the same chip in 2 completely opposite ways, which is why inference hardware and training hardware are diverging. So, NVIDIA still holds about 80%, but custom silicon is growing fastest. Memory bandwidth, not raw flops, is the constraint that decides real performance. The network is around 15% of the cost and most of the bottleneck. And the biggest cluster on Earth doubles every 7 months. If you haven't seen part 1, it explains how the chip itself actually works, the warps, the latency hiding, the tensor cores. Subscribe, and I'll see you in the next one.